Hi there, everybody. In this section, we're going to finish up Chapter 5, and we're going to look at making connections. This is basically, it ties together all the material from Chapter 3 and Chapter 4 so far. So that's what we're going to be doing today. So in Chapter 3, we see that a confidence interval gives us a plausible range of values for the population parameter. In Chapter 4, we use a hypothesis test to determine whether a given value in a null hypothesis is plausible or not. We can use a confidence interval to make a decision in a hypothesis test, and we can use a hypothesis test to determine whether a given value will appear in a confidence interval. So we're just going to look at what the difference is between the two and when you would use one compared to another. So for a two-tailed hypothesis test, the confidence interval is related to the significance level alpha using this straightforward equation. The confidence level is just 100% minus alpha. That should make sense, right? Both of these distributions, the bootstrap distribution and the randomization distribution, we use them because we can rely on the 95% rule for bell-shaped distributions. So it makes sense that there would be some sort of relationship between them. It might not be obvious what it is up to this point, but now you know the relationship. So when the null parameter value falls outside of a 95% confidence interval, then it is not a plausible value for the parameter, and we should reject the null at a 5% level in a two-tailed test. When the null parameter value falls inside a 95% confidence interval, then it is a plausible value for the parameter, and we should not reject the null at a 5% level in a two-tailed test. So what does that mean? Well, let's see on the next slide exactly what that means. So here we have hypotheses for a statistical test are given, followed by several possible confidence intervals for different samples. In each case, use the confidence interval to state a conclusion of the test for that sample and give the significance level used. So if we're testing mu equals 15 against mu not equal to 15, the idea is, what does this confidence interval tell us about the believability of 15 versus not 15? So two-tailed test and then confidence intervals. Notice the confidence level is important because we have to state the significance level, right? So this tells us whether the null parameter, that's 15 is the null parameter, either one, it's the same number. And we just use the rule on the previous slide. If this number is in the confidence interval, then it's believable or plausible, and if it's believable, then we do not reject the null hypothesis. So 15 is in this interval, which makes it plausible, so we do not reject. But what is the significance level? Well, we have to use the formula. The formula says it's 100% minus the confidence level, right? So look here, right? So we're trying to figure out what alpha is. Well, if our confidence level is 99%, 100 minus 99 is 1%. So alpha is 1% or 0.01 for this problem. So this would be, do not reject the null hypothesis at the 1% level. Let's keep moving. Let's look at part B. Here's a confidence interval from a sample, and here's a 95% confidence interval. So does this confidence interval tell us to reject or not reject this null hypothesis? Well, is 15 in the interval? It is not. That tells us to reject, right? That means mu is not 15. It's some other range of values that 15 is not included. And again, 100% minus 5% gives us 95. So we do not we reject the null hypothesis at the 5% level. Right? It's not within the confidence interval. So 15, the null parameter value. And last one, part C. Our 90% confidence interval is 13.5 to 16.5. This is another do not reject. 15 is in the interval. and we do not reject at the 10% level because 100% minus 10% is 90%. So that's pretty much all you have to do for this stage of the making connections. Most of your homework deals with something like this, but there's more going on than just this. We're going to tie up all the loose ends from chapter 4 so far, because there's a lot of loose ends. Now, what if we have a one-tailed test? So the relationship is slightly more complicated. And the reason is that a one-tailed test only looks on one side of the null parameter, right? And it ignores everything on the other side. But a confidence interval always has two sides. So what we have to do is you have to take that alpha value and double it so that it matches up with a confidence interval. Remember, one-tailed test only has one tail. Confidence intervals always have two tails. So you need to double alpha so that the tails are the same size. So other than that, it's pretty much the same thing. The most complicated thing is this, but there is an additional qualification. So first thing is the same as what we just did in example 1. The null parameter needs to be outside of the confidence interval, and the confidence interval needs to provide evidence in support of the alternative. If the confidence interval does not support the alternative hypothesis, even if the null parameter is outside, then you do not reject. So it is more complicated. On the homework, you might not really notice how much more complicated it is, but make sure that you're looking at one tail versus two tail as the first step when you're trying to connect intervals and these tests. All right, example 2, a confidence interval for a sample is given, followed by several hypotheses to test using that sample. So here, in example 2, we're reversing the type of problem. Here, you're given the confidence interval, and we have lots of hypotheses. In example 1, we had one hypothesis, or one set of hypotheses, and multiple confidence intervals. So in each case, use the confidence interval to give a conclusion of the test if possible, and state the significance level. So these are all going to be one-tailed tests. So the significance level is going to be the same for all of these. So let's look here. Our confidence level in example 2 is 90%. So what's alpha going to be? Well, 100% minus 2 times something is 90%. You can do algebra if you want, but you're not going to need to because alpha would just be 5%. So 100% minus 2 times 5% is 90%. So the alpha value isn't going to change. It's the same for this whole problem. What is going to change is reject or do not reject. So if the null hypothesis is p equals 0.5 against p greater than 0.5, look at the null parameter value. 0.5 is in the interval, so we do not reject. And again, alpha is 5%. Right? Let's look at B. P equals 0.75. And the alternative is P is less than 0.75. So 0.75 is not in the interval, but that's not enough. We have to check that every value in the interval supports the alternative hypothesis. So is every number in this interval less than 0.75? It is. So that tells us to reject this in favor of this. Every number in the interval supports this. None of these numbers support this. So this is reject the null hypothesis at the 5% level. So 0.75 is not plausible because it's not in the interval, and every value in the interval is less than 0.75. So again, when you're doing a one-tailed test, you have to check two things, not just one. And then part C, P equals 0.6. 0.6 is not in the interval, but we have to check Does every number in this interval support this alternative hypothesis? No. The alternative hypothesis here is greater than. All of these numbers are less than. So even though 0.6 is not in the interval, this is a do not reject. You need to check both things for one-tailed tests. So even though 0.6 is not plausible, the confidence interval is on the wrong side of the alternative hypothesis, right? Every value in the interval is less, so we can't support the alternative hypothesis that p is greater than 0.6. So just so everybody knows, this is one of the more difficult topics we're going to do the whole semester. Because you have to check so many boxes. If you're having trouble with this, that's okay. You can ask questions in class. But don't be discouraged if you can't get this right away. Because it's not used very often. You do have to know it for the test, but it's not used very often sort of later on in the class. All right, let's keep moving. So now we want to know, when do we use confidence intervals compared to when do we use hypothesis tests? So confidence intervals describe the magnitude of an effect, such as the size of the difference in population means. These are used mainly in observational studies such as surveys and election polling. Hypothesis testing is a formal comparison with a pre-specified hypothesis and significance level. These are mainly used in experimental studies such as medical testing with blinding in a control group or in industrial settings when the population parameters are known. So just roughly speaking, confidence intervals are a lot less formal. All you need is a representative sample and you can make a confidence interval. It often does not require a lot of formal planning, and some, but not as much as some of the experiments we've seen. Hypothesis testing is usually associated with a much more formal setup with randomized experiments. Now, that's just a generalization. Hypothesis tests can be used with observational studies, and it happens all the time. Confidence intervals can be used with hypothesis testing. It happens all the time. But if you're not sure, this is a good guideline. So for each of the following scenarios, indicate whether it is best assessed by using a confidence interval or a hypothesis test, or whether statistical inference is not relevant to answer it. So remember, statistical inference is using information from a sample to learn about a population. And the assumption when we use statistical inference is that the population is too big or poorly defined to be reached directly. So we have to pass through just a sample. That's the idea. If we're using statistical inference, it will be a confidence interval or a hypothesis test. All right, A, is there a difference in the headache rates of Nasonex users compared to placebo? So look at the question the way it's asked. So let's determine if we need statistical inference. Well, Nasonex is a very popular decongestant drug, so there's no way we have access to the millions of people that use Nasonex. So statistical inference would definitely be needed. Researchers would have to acquire a representative sample and then do the testing. But could we use a confidence interval? Well, remember, confidence intervals are best used to estimate the size of an effect. Here, we're not asked anything about the size or what is the difference between these. It's saying, is there a difference? So we're answering a question, and it's essentially a yes or no question. Well, hypothesis tests are perfect for answering yes or no questions. Either a significant difference exists or it doesn't. So this is a hypothesis test. Part B, what % of U.S. voters support instituting a national kindergarten through 12th grade math curriculum? So again, do we need statistical inference? Well, we're talking about U.S. voters. That's a very large group. So we would need to use statistical inference, take a sample, and estimate the population parameter. But could we use a test here? Well, notice it's not saying, remember, a test, you need to have a claim, right? There's no claim here. It's not saying, is it true that more than 50% of voters favor this initiative? It doesn't say that. In the previous problem, it does say that. The claim is, we're testing whether a difference exists or it doesn't. Here, there's no claim, so this is a confidence interval. So, statistical inference, confidence interval. And C, what is the mean GPA of students in this class? So, do we need statistical inference? Always start there. Well, the class isn't very big, right? Your class is 24 students at most, depending on which of my classes you're in. And if we wanted to estimate that, we could take a sample. Or I could just post something online and everyone could answer it anonymously. So I do have access to the population, so I don't need statistical inference. If researchers have access to the population, inference is not relevant or not needed, I guess you could say. All right, let's keep moving. So let's talk about why tests and intervals have the relationship that they do. So in section 4.3, we saw a randomization test for the proportion P of adults in Lorain County who own a smartphone. It was determined that the results for the sample statistic of 0.87 were statistically significant. We had a p-value of 0.038. So that caused us to reject the null hypothesis and accept that P is not equal to 0.81. Notice we would get the same results using a confidence interval centered at P hat. So here's a picture of the two distributions, and I just overlapped them to show you how this works. So here is our randomization distribution. The null hypothesis is 0.81, right? It says right here, null hypothesis 0.81. So if 0.81 is indeed the proportion of Lorain County residents, adults who own smartphones, then this is the distribution of sample statistic we would expect to see if we took lots and lots of samples. Now, I'm just using the 95% rule here and showing you that the red dots are these rejection region. So that corresponds to a two-tailed test with an alpha of 5%, right? Because we just add up the rejection areas to get 5%, right? So what this is saying is that if 81% is the population parameter, then we would expect to see 95% of sample statistics from that population between 0.755 and 0.865. So again, it tells us about the distribution of sample statistics. Now, the bootstrap distribution comes from a single sample. The sample in question here is this p hat equals 0.87, right? So the randomization distribution, 0.87, is in this red region here because it's outside the middle 95%. But the bootstrap distribution is centered at 0.87, right? Because a bootstrap distribution, you start at the sample statistic and then you build a sample with replacement. And we know how to do that. We saw that in chapter 3. So here's the sample statistic, 0.87. And then a 95% confidence interval would be 0.82 to 0.915. So we can interpret both of these. This one, we interpret using the null parameter value. This one, we interpret using the sample statistic. And you'll see that they give us the same answer. And we talked about this early in chapter 3, how it makes sense that we should be able to shift these things around, just scoot them around, and they should maintain their shape. There's no reason to believe that they would change shape if you have large enough samples, right? We mentioned that you need to have sufficiently large samples. Here the sample is certainly large enough. So what exactly is going on? Well, the bootstrap distribution from 0.87 got us a p-value of 0.038. That tells us to reject the null hypothesis. Why is that? Well, what we saw earlier in these notes is that if your p hat value is outside of your of the 95% interval generated by a randomization distribution, it'll be one of these red dots. So we already know how that works, right? That's how we did stuff in chapter 4 so far. But what we saw in this section is if the null parameter, 0.81, is outside of the 95% confidence interval, that's also telling us to reject the null hypothesis. So the two ideas match. So here, 0.81 is this green line. And you can see down here that it's outside of our confidence interval. The confidence interval is 0.82 to 0.915. I just made a 95% confidence interval. 0.81 is on the outside. That tells us that the null parameter is not believable based on this sample. And that would tell us that the population proportion is different from 0.81. Again, that's given here on the previous slide. Right? So that tells us to reject the null hypothesis. Also, we know how randomization distributions work. 0.87 would go right here, and we can see that the p-value for 0.87 is going to be less than 5% because 5% of these dots are red, and 0.87 is here. It's farther out than some of the red dots, so its p-value would be lower because the p-value counts how many dots are at that value or farther away. So there you go. So that's how it works. This also does explain why a one-tailed alternative hypothesis requires us to double alpha in order to match it up with the confidence interval. You can see it here. If this were a one-tailed alternative hypothesis, let's say to the right, we'd only be counting 2.5% of the dots. So the alpha value would be 2.5%. But the confidence interval is still 0.95. It's still a 95% confidence interval. So we have to double this so that it matches the corresponding confidence interval. Again, sort of a difficult concept to understand. Think about this. If you go back and were to go to Chapter 4, all the stuff we've done in Chapter 4, if you were to take the sample statistic and build confidence intervals with that sample statistic using a bootstrap distribution, you would get all the same answers. Every time you reject the null just using the sample statistic, you would also reject the null with a confidence interval and then checking the null parameter in the confidence interval. Alrighty, let's keep going. So we're going to talk more about randomization distributions. The rest of this video, we're going to discuss how randomization distributions are built, and we're going to look at how to do at least some of the different kinds we haven't discussed. I don't have time to go over every single randomization distribution because there's 5 kinds. There's really too many to go over, but I'm going to go over a couple of them. So we've already seen how to do a randomization distribution for a difference of population means, right? So the example we saw how to do was the caffeine and finger taps example. We randomly sampled both groups after they've been combined. That's the most common method. It's not the only method. StatKey comes with lots of methods built in, and we're going to see a couple of these. This is because we're presuming that the population means are equal, and therefore the particular assignment of each subject to a treatment has no effect on the parameter, right? So if you're randomly assigning values, then mu1 minus mu2 should be close to 0. It's going to have some variation, but it still should be centered at 0. So let's talk about some other distributions. For a single quantitative variable, each randomization sample is randomly selected with replacement from the original sample. So that's like a bootstrap distribution. But we do this after each data value has been adjusted to conform to the null parameter value. So this is by far the most abstract thing we cover in this class, at least till chapter 6, at least up to this point, because it's hard to see why we need to do this. So the randomization sample is the same size as the original sample, but comes from a population with a mean equal to the null parameter value. So what we're doing for a single quantitative variable is we're basically doing bootstrapping except we are scooting the parameter, so the center of the distribution, until it matches the null parameter value. So let's see how that works. So here's a nice little example I did in StatKey just to show you how it works. So let's say our original sample has data values 1, 2, 4, and 9. So here they are, 1, 2, 4, and 9. So the mean of this distribution is 4, right? Because this adds up to 16. So the sample mean is 4, right? Nothing fancy going on there. If we were to do bootstrapping, we would sample with replacement from this, and we would get a distribution. And maybe it wouldn't look so great, but we'd get a distribution. So let's say the null hypothesis is that mu equals 6, and this is a sample from a population where we suspect that mu equals 6. So how do we do a randomization distribution? Well, the null parameter value is this number. So each value in the original sample is increased by the difference between the null parameter value and the sample mean. So 6 is 2 units bigger than 4. So we increase each of these by 2 units, just scoot them to the right on the number line, 2 units. Then we sample with replacement like it's a bootstrap distribution. And so that's what I did, right? So here we go. So you can see here that I did sampling with replacement after these values were scooted to the right, and I got 3, 4, 4, 6. So 3 came from the 1 after it was scooted to the right 2 units. So 1 plus 2 is 3. Both of these 4s, I'm allowed to have multiple 4s because it's sampling with replacement. These are the 2s scooted to the right 2 units. 2 plus 2 is 4. And I got a 6, which is 4 plus 2. And then this has its own sample mean, this randomization mean. You would plot that on a dot plot, and you would repeat. And so with one quantitative variable, randomization and bootstrapping are essentially the same process, except the randomization, you just scoot a little bit to the right or left, depending on the relationship between the sample statistic and the null parameter value. So that one's actually not too bad. This is what I just described. For a single quantitative variable, the randomization process is similar to bootstrapping with the exception that the data values are shifted so the original sample mean is equal to mu0 before they are randomly sampled. Randomization distributions for a single proportion are computed similarly with the original data values shifted to p0 before they're randomly sampled. So we already saw in chapter 3 how to do a bootstrap distribution of this type, and we've seen some other ones as well. So if you go back and look at any of the examples we've done with randomization distributions or bootstrap distributions with a single categorical variable, so proportions are very similar. The values are adjusted, then sampled with replacement. So one variable randomization distributions are both just like their bootstrapping counterparts, except some adjustments are made before sampling with replacement. When you have, so that's 2 of them, when you have 2 variables, you use the process we used in example 1 in section 4.2, the caffeine and finger tapping example. So when more than one variable is involved, the data values are combined and then randomly assigned to the different groups. This is similar to example 1 regarding the difference in the mean finger taps. Randomization distributions for difference of proportions and correlations are computed similarly. The data values are combined and then randomly assigned to the different groups. So what we did with the caffeine and finger tapping, and if you forgot, just pause this and go back and look, because you have to understand this or you won't know what's going on. So with the caffeine and finger tapping, the idea was we took all the response variable values, put them in a hat, drew out 10 randomly, and called that the caffeine group. The other 10 randomly, we called them the placebo group. We computed the means of each group, subtracted the means, plotted the difference of means on a dot plot. Well, it turns out we do the same thing for proportions and correlations. With proportions, it's really easy. You just take the response variables. In this case, those are like yes or no answers, right? If it's categorical, right? Or male, female, right? Whatever your categorical explanatory variable is, you just take all the responses and randomly assign them, just like we did, and then compute the proportions, subtract the proportions. So that works pretty easy. The one that's hard to kind of imagine how it works is the one for correlations. So we're going to see a correlation example here. And my picture's too big. Ooh. All right, there we go. So this graph below, this is the number of hurricanes that made landfall on the east coast of the U.S. during the years 1914 to 2014. So even though this is not a random sample, we're just going to treat it as a random sample. And we want to know, we're going to answer the question, does it appear as if the number of hurricanes is increasing over time? So if we're treating this sample as its own population, obviously it's increasing over time. We can see that the slope of the regression line is positive. But if we want to generalize this to, all years, so including years outside, and you might think, wait, we can't do that. We're allowed to do that when we do inference. We weren't allowed to generalize outside the regression line when we were doing descriptive statistics, which was in Chapter 2. Since we've been doing Chapter 3 and beyond, we're doing inference where you are allowed to take the values outside. So I know some of you might be thinking that, how can we use that? How can we use values on the outside? All right, so does it appear as if the number of hurricanes is increasing over time? So here's the sample correlation. So the way this works is every year has exactly one number of hurricanes that made landfall on the east coast of the US. And again, that counts Gulf of Mexico and everything. It's just, everywhere that there's water, east of Texas in the US. So the idea is, how do we do a randomization distribution here? Well, turns out it might be hard to imagine how it works, but after I show you, should make sense. So the way we do it is we match all the 101 data years to a random number of hurricanes contained in the original sample. So what it is, it's a one-to-one correlation. There are 101 data years from 1914 to 2014. Right? And there are 101 values that represent the number of hurricanes of a particular year. So what you would do is take the 101 data years, put them in a hat, and say, okay, we're going to pick one out of a hat and match it to 1914. Pick another one out of the hat, match it to 1915, and just keep going until the last randomly selected data value is matched to 2014. After each of the data values have been randomly paired up, the randomization correlation is computed. So you have a random matching of these values, and then you plot those on a scatter plot, compute the correlation, and plot the correlation on this graph. So there's a lot going on there, but it should make sense. So here are 1,000 randomization correlations made up by pairing up the original sample data in a random way. So the reason we use these randomization distributions is to find out how much variability there is, right? If you have a large enough sample, you're going to get a bell-shaped distribution here. But we want to know how much variability is there because we want to do a hypothesis test. And how do we do that? Well, we know how to do it for all the other statistics, so we're going to do it the same way here. You find the original sample statistic. In this case, it's the correlation, right? This is a sample statistic. So we just have to plot 0.306 on this graph somewhere. Well, it's way over here. And then we're going to do a randomization test of rho equals 0 versus row greater than 0. Why is this greater than instead of not equal? It has to do with the original problem. Go back 2 slides. Does it appear as if the number of hurricanes is increasing over time? We have an increasing here. That tells us that the slope of the regression line is positive, which tells us the correlation is positive. So we're looking to see whether the data provide enough evidence of a positive correlation. So that's why we have rho greater than 0. Well, 0.306 is way over here. So you're going to get about 2 dots out of 1,000, right? And 2 dots, oh, here it is up here. There are 2 dots at least as extreme as 0.306. So here's 0.306 right here. Move to the right, 2 dots. So the p-value is 2 out of 1,000, or 0.002. 0.002 is going to be less than any alpha value we pick. So that is strong evidence to support the alternative hypothesis that a positive correlation exists between the number of hurricanes for all years. So you can see that the method we're using here is the same one we used for all the other randomization distributions in Chapter 4. It doesn't change. And this would also be the same thing we would use if we were doing bootstrapping, which you could do, except it would be centered at the sample statistic. But other than that, it would be the same. Sampling with replacement. All right. Well, that's it for section 4.5. So that's all of the, so we've covered all of the material that's going to be on exam 2. There is a lab, and the video's up for the lab. And there is going to be review material posted as well. So on the week of the exam, because I don't know when you're watching this, but on the week of the exam, you will have 2 different review sheets, just like you had for the first exam. All right, so that's it for today. If you have any questions, let me know. And here's some extra practice for you. It's not a ton, because there's really not that much new stuff in this section. There's really only 2 new concepts. Everything else is based on stuff we did earlier. So stay in touch, and I will see you next video. Bye-bye now.